Hello friends, in class 12th, the P block elements, we were discussing about group 17 elements, and in this video we will discuss about anomalous behavior of fluorine and reactivity of halogens towards hydrogen, oxygen, metals and other halogens. First, anomalous behavior of fluorine. As we have discussed that fluorine is the first member of group 17 elements. Okay, ionization enthalpy, electronegativity and electrode potential are all higher for fluorine than accepted from the trends set by other halogens. Also, ionic and covalent radii, melting point, boiling point, enthalpy of bond dissociation and electron gain enthalpy are quite lower than accepted. The anomalous behavior of fluorine is due to its small size, highest electronegativity, low FF bond dissociation enthalpy, and non-availability of d orbitals in valency shell. Most of the reactions of fluorine are exothermic. Why? Due to small and strong bond formed by it with other elements. It forms only one oxo acid. What is this oxo acid? We will discuss in next video. While other halogens form a number of oxo acids. Hydrogen fluoride is a liquid. Due to strong hydrogen bonding, hydrogen bond is formed in HF due to small size and high electronegativity of fluorine. Reactivity towards hydrogen. They all react with hydrogen to give hydrogen halides, that is HX. But affinity for hydrogen decreases from fluorine to iodine. You can say that is fluorine is most reactive towards hydrogen and iodine is the least reactive towards hydrogen. Hydrogen halides dissolve in water to form hydrohalic acids. For example, HCl. If this is in gaseous form, this is called hydrogen chloride. But if it dissolve in the water, then this is known as hydrochloric acid. And if we compare their acid strength, then acid strength of these HX increases down the group. That is HF is the least acidic and HI is the most acidic. And this acidic nature can be explained on the basis of their stability. The stability of these halides decreases down the group. HI is the least stable and HF is the most stable. Again, this stability depends on their bond dissociation enthalpy of HX bond. And this is decreases like this. That is H for HF bond dissociation enthalpy is maximum and for HI the bond dissociation enthalpy is minimum. And again we can say this bond dissociation enthalpy is related with the bond length. As the bond length increases down the group, bond dissociation enthalpy decreases down the group. Hence stability decreases down the group and acidic strength increases down the group. Clear, student? Now come to the melting point and boiling point. General trend is this is melting point and boiling point is increases from top to bottom. But again exceptionally HF, see HF in both the cases exceptionally high melting point and boiling point due to the formation of hydrogen bonding. Is it clear? Reactivity towards oxygen. Halogen forms many oxides with oxygen, but most of them are unstable. Fluorine forms two oxides, OF2 and O2F2, and only OF2 is thermally stable. But again, remember, most important point is actually these are not oxides. These are known as fluorides, oxygen fluorides. Why? Why oxygen fluorides? Because of the higher electronegativity of fluorine than oxygen. That's why OF2 and O2F2 are not considered as oxides. These are named as fluorides. Both are strong fluorinating agents. O2F2 oxidizes plutonium to PuF6 and this reaction is used in removing plutonium as PuF6 from spent nuclear fuel. Actually plutonium is used as a nuclear fuel in nuclear reactor. Okay, and this reaction is used in that case. Chlorine, bromine and iodine form oxides in which the oxidation states of these halogens range from +1 to +7. A combination of kinetic and thermodynamic factors lead to general decreasing order of stability of oxides found by halogens in this order. That is Oxides of iodine is more stable than chlorine, and oxides of bromine are least stable. Okay. Higher stability of oxides of iodine is due to greater polarizability of bond between iodine and oxygen. In the case of chlorine, multiple bond formation between chlorine and oxygen takes place due to availability of d orbitals. This leads to increase in stability, and bromine lacks both the characteristics. Hence, stability of oxides of bromine is least. The higher oxides of halogens tend to be more stable than the lower ones. Now again, if we compare these oxides, chlorine oxides Cl2O, ClO2, Cl2O6 and Cl2O7 are highly reactive oxidizing agents and tend to explode. ClO2 is used as a bleaching agent for paper pulp and textiles and in water treatment. The bromine oxides Br2O, BrO2, BrO3 are the least stable halogen oxides as we discussed, and this is known as the middle row anomaly. Okay. Now you can say in the periodic table, see this, in the periodic table of the elements, the phrase middle row anomaly refers to the relative instability of bromine oxides compared to other halogen oxides such as oxides of chlorine and iodine. And that's why they exist only at low temperatures. They are powerful oxidizing agents. The iodine oxides I2O4, I2O5 and I2O7 are insoluble solids and decompose on heating. I2O5 is a very good oxidizing agent and is used in the estimation of carbon monoxide. Reactivity towards metals. Halogen react with metals to form metal halides. For example, bromine reacts with magnesium to give magnesium bromide, like Mg plus Br2 gives MgBr2. The ionic character of the halides decreases in the order. That is, Mf is highest ionic character and Mi is lowest ionic character. What is the reason? We can see more difference in the electronegativity, more the ionic character. Being fluorine most electronegative, that's why highest ionic character in metal fluorides, and iodine is least electronegative in this group. That's why metal iodides have the least ionic character. Okay, where M is a monovalent metal. If a metal exhibits more than one oxidation state, the halides in higher oxidation state will be more covalent than one in lower oxidation state. Try to understand. If a metal exhibits more than one oxidation state, okay, we can say higher the oxidation state, higher the positive charge. More the positive charge, more polarizing power. And according to the Fajan's rule, more polarizing power means more covalent character. Is it clear? That's why in higher oxidation state, compounds are more covalent, and in the lower oxidation state, compounds of the same metal have less covalent character. We can understand by example like SnCl4, PbCl4, SbCl5 and UF6 are more covalent. Then SnCl2, PbCl2, SbCl3 and UF4 respectively. You can say in SnCl4 its oxidation state is +4. In SnCl2 its oxidation state is +2. Okay, this higher oxidation state, that's why more covalent. Reactivity of halogen towards other halogens. Actually, halogen can react with the other halogens, and in this way, whatever the compounds formed, these are known as interhalogen compounds. We will discuss separately about these interhalogen compounds. Different type of interhalogen compounds are formed, like X, X-, X, X-3, X, X-5, X, X-7, where X is a larger size halogen. Clear? And X dash is smaller size halogen. We can say like a larger size halogen IF7, okay, BRF3, F3. These are the some examples of inter-halogen compounds. Okay, student. Thank you.